I induced some faults in a small motor because none of you will ever let me have your data or just test on your equipment. So we should work on that. But here's my little dyno. I have 2 drill motors, and I just hooked one motor up to a resistive load. So it's kind of like a constant torque dyno. I have the other motor hooked up to my inverter, which is just the trigger of the drill hooked to a battery, and I'm making voltage and current measurements on the 3 phases. In one test, I induced a short circuit fault, and as it looks, I shoved a soldering iron into the winding and I put some solder in there, and that is a induced fault. So that's a little bit of solder and a whole bunch of melting. For the demagnetization, I took a different rotor and stator, and I cooked that magnet. I mean, I got it hot. And then I put a ton of current at it, and I induced a demagnetization. Not the most scientific faults induced, but I think the data will show for itself. So what was my test procedure? I characterized the healthy state, and I just ran it through a profile of different speeds. I made sure I got certain speeds for every test. Because my dyno is this resistive load, it's basically a fixed torque and fixed current output, so I'm pretty safe there since I did not change the characteristics of the load motor. I then did the exact same characterization for the short circuits and the exact same characterization for the demag. We can see here, this is my eDrive system where I recorded my currents, my voltages, and all my fun measurements. This is my little dyno, here's my load, and here is my inverter battery. Again, very scientific. You got to work with what you got. So what's a test example? I ran the different profiles at different frequencies from 0 to max frequency. I measured the inverter currents. These are my RMS currents, my RMS voltages. This was from the healthy test. This is a screenshot from our software. I calculated the RMS values, the power and reactive power, the total harmonic distortion, and the 0 sequence voltages. And what did I see? So here I have plotted the 3 phases of healthy, the 3 phases of short, and the 3 phases of demag for the phase currents. Well, my demag and my healthy look pretty similar. They're both right here. But my short circuit, if we look at my RMS current, it's just to the moon, and this is that phase imbalance. So we can very easily see that, okay, I have a turn short, I can identify that right away. That's a no-brainer. Also, if I look at my 0 sequence voltage, my healthy and my demag, with some mathematical analysis, we could probably determine that these two were statistically different, but that short circuit's just screaming, like very easily monitor for this. So we see increases in voltage, increases in current, increases in input power, increases in 0 sequence voltage, and the power factor was just crazy. I wanted to plot that, but it was just nonsense, which is an indicator. How about demag? So we can identify short circuit current. Cool, that was easy. Demag, we're going to see an increase in voltage, an increase in current, an increase in input power, and a disturbance in the 0 sequence. And what I've plotted over here I think is pretty interesting. So again, I left this turn-to-turn short circuits in here just to demonstrate that like phase voltages also all over the place for my short circuit. But let's look at our healthy in blue and our demag in green. My healthy is here, and my demag has an increase on the input voltage. Why an increase on input voltage? Well, the flux on my rotor is smaller, so I need to provide more voltage on my stator, more voltage from my inverter to provide that same flux to get that same torque output. So we see, this is subtle, but not that subtle. We can start to see this failure creeping up. This is really cool. We can see that little tiny failure, and I'm pretty sure this was an asynchronous, but we see that. That's statistically notable. That's cool. We can also look at the reactive power. And again, short circuit current all over the place. But I've got my demag in green and my healthy in blue. And we can see that the reactive power looks pretty similar until I get to a certain speed. And then we can see that deviation. Again, we can find multiple sources for these faults and start to identify what their cause was and where they're located. I thought this was super cool when I looked at the data, and it was like, oh, these are the same. Nope, they deviate. Really cool stuff. And this was not the most scientific test ever, but it very clearly shows this. And if you had an advanced post-processing tool and some knowledge of the FEA, you could do some really cool stuff. So with that, I went a little